With the discussion we have had so far, we can say that any polynomial actually takes this generalized format. You can check with the examples that we have done so far, and if you look at them closely, you will find that they all have this generalized format. Okay. Now, our Bairstow method wants our f of x to be rearranged in a way so that we can have one quadratic equation at one side and another q of x at another side, and we after that we will shift our focus to the quadratic equation and solve the quadratic equation. Okay, to get the quadratic equation and or to rearrange the f of x into that way, we need to start with some values of u and v. Okay, so look here, this is how we get to see our setup. And then with the examples we have done so far, we have seen a pattern exists, and that is somewhat like this. If this value goes down and then we multiply u with this value and put it here, again we multiply this value with this u and then put it here, and so on and on. So this is how the format or the generalized format looks like. The qx has these coefficients and the remainder has only these two values. In order to apply our Bairstow method, we want our remainder to be 0. So our main focus is here. If you look at this portion, we can rewrite this bn to be this and bn minus 1 to be this, which in return tells us that any value of the b has this generalized format. Okay. Our main goal is to establish that this value becomes to choose u and v such that these things become 0 and these things become 0. So the main idea here is that we are now left with these two equations, and we want this value to be 0 and this value to be 0, which eventually gives us a system of nonlinear equations. We can say that if this value in total becomes 0, I mean if this becomes 0, that means this is one function that is a function of u and v, where u and v are our variables. And if this equation becomes 0, this is another function of u and v. And this is a system of nonlinear equations. And we have had a little bit of discussion about systems of nonlinear equations. And we said that we have to apply modified Newton-Raphson method to solve these types of system. If you do not remember that, I think you can remember up to this that solving these types of equation require these values to be found. So from this setup, we need to calculate these derivatives. We need to calculate the change of Bn with respect to u, change of Bn with respect to v, and same thing here. We have to look at the change of this function with respect to u, change of this function with respect to v. How we can calculate these changes? Let us focus here. This is the generalized format. If we look here at b0, is there any change with respect to u? Because as this is the very first value, there are no change available and there are no change with respect to v as well. If we shift our focus to b1 here, what is the change here at the value of b1 with respect to u? There are some change with respect to u, that is b0. And is there any change with respect to v? No, there are no change respect to v, which is 0. Why we are doing this? Because this is important. We will have to fill the gaps or find a pattern to keep our calculation going. What about B2? What are the changes with respect to U? With respect to U, we have here this change. And with respect to V, we have only B naught, which is equal to this thing. So we can generalize that this change in B with respect to U in this way. If any change occur with respect to U, this has this pattern, and we can denote this thing as a new quantity, which is C. Now the question is, how can we calculate C? We have seen calculation of A, it comes from the polynomial itself. We know the calculation of B, it comes from the calculation after we apply the Ruffini's method. How we can calculate these values of C? We will calculate these values of C by applying the Ruffini's rule again into this B. If we are given a function, then we know the values of A is A naught, A1, A2, AN minus 1, AN, and we will start with some assumption of UV. And from these assumptions, we will eventually have these values of B0, B1, B2 up to Bn. If we apply again the Ruffini's rule here by setting things up with U and V, then we have these calculated values are C. And these values of C are essentially the derivative of B with respect to U and V. To keep our calculation going or to have things in our control, we imagine these two values as the temporary values, which are C minus 1, which is C minus 2. Now, I think this will start to make some sense. After applying Ruffini's rule, we reach this point where we have these two equations of nonlinear systems, and our goal is to make this value 0 and make this value 0. In doing so, as we are solving nonlinear systems, this will generate two derivatives and this will generate two derivatives. This derivative we have derived with some other values of C, and we have seen how we can calculate these values of C, right? Now, if we plug all these things into these equations again, they turn into this. If we solve this equation, then we get the values of del U and del V. So, everything comes into this point that we will be given one f of x, and from that f of x, our target will be to convert that f of x into a certain format where the remainder is 0. To get that remainder, to get that format available to us, we need to choose u and v very carefully. So obviously at the first iteration, we might not reach to a level where the remainder is 0. So we have to run iterations, and running the iterations will lead us to exact values of u and v that returns the remainder to be 0. Here we can see after one calculation we get some values of del u and del v that we will apply to our assumed u and v, and then we get our next iterative values of u and v. And in this way we will again run the setup and again we will get some del u and del v. till we reach to a point where the del u and del v are very negligible, and we do not have to change our uv or our iterated values of uv. Then we can say that we have reached to a point, we have got a certain values of uv. That means we are now good to go with this equation x square minus ux minus v. If we solve this equation, then we will get two roots. So that is our main idea. After we have calculated roots from this equation, we will shift our focus into qx. In that qx, we will again convert it into such a way so that we get some x square minus ux minus uv, and then so on and on. In this way, we will run our Bairstow method, and we will try to reach to a point where we can calculate all the roots of any given polynomial. So that was the basic idea of Bairstow method, or the theoretical idea how Bairstow method will be applied. To solve any mathematical problem, you might not need all these understandings. If you just know the formulas, you can plug the values into formulas and do the math. But our main goal is to understand the numerical methods or the logic that goes behind it before blindly running behind formulas and plugging things into a formula and getting the results. So that was my attempt to make you understand what goes behind when we try to apply the Bairstow method. Thank you very much. Then we will see one mathematical example using this theoretical knowledge.